Telephone fluid mechanics.
What's telephone fluid mechanics?
Like turning mixing, and you just turn them around.
Oh.
And you just mix them around.
Okay.
So you touch the forest.
Welcome to video number 19 in fluid mechanics. So in this video, we're going to be starting section 7, which is external incompressible viscous flows. In section 6 that we just finished, we did internal flows, which were flows like through pipes and ducts. External flows in section 7 are going to be flows around objects. So we're going to be looking at flows around things like vehicles, aircraft, wings. We're going to be looking at different sports balls, so baseballs and golf balls as well. And specifically in this video, we're going to start in part A, where we're going to look at boundary layers. And so that'll cover off the fundamental concepts that really govern the behavior of flows around objects. Okay, and this is the breakdown of section 7, with the white text showing what we're going to cover in this video. Basically, we split it up into two parts, part A and part B. So we'll do part A in this video. We'll talk about boundary layers. Then there's a short example 7.1 comes after this video. That'll be in a separate video. And so basically what makes up part A is we first need to look at boundary layers. And I think the best way to set the stage, for what's coming up here in section 7, to give us something to continually refer back to, is to take a look at this airfoil here. So race cars usually have wings on them, sometimes even two, one at the front, one at the back. And of course, airplanes is the other place where we're gonna see airfoil. So what we can think of, we're looking at here with this airfoil, is basically a slice, like a cross section of a wing. And I'll show a video in a second. And so what I want us to do is take a look at this labeled figure here. And then when I play the video, I'll narrate on top of it with my cursor, and we can actually see all these things in an actual flow. So the first thing is, as you have the flow, you have basically this free stream velocity, right? So this flow before it hits the wing is going to be nicely distributed. Then as it approaches the wing, the flow has to change to get around the object itself. So first thing we're going to come across with is a stagnation point right here. Stagnation point means the place at which the flow stops, or the flow becomes zero. And what we can think of that is sort of dividing the flow. So above that, the fluid above that goes up, and the fluid below that goes down and around the bottom. And that stagnation point is the point where the flow comes to a velocity of zero. Anything below goes down, anything above goes up, right? Then we have LBL labeled here. So what happens is, it's like the same thing we saw in pipes, right? When you have a solid surface, any air particles, now let's say going upwards, right? Any air particles right against this solid surface are gonna have the no slip condition, because that surface is not in motion. So the particles right against it can't be in motion either. So we have the no slip condition there. And then again, similar to pipes, right? We're gonna have those frictional effects grow larger and larger into the flow as we get greater and greater shear. So we have the LBL means laminar boundary layer. We also see that labeled down here, laminar boundary layer. And for starters, we note about this figure, like that's drawn much larger than it actually is, just for visualization effects. So don't think at all that that's how thick the actual boundary layer is. It's much, much thinner than that. And what they're sort of trying to show here with the dashed line, that's the edge of the boundary layer. We can see it sort of growing. We remember the same way with pipes. So that will grow as you move along the surface, because those frictional viscous effects influence a larger and larger proportion of the flow as you move along the surface. Then T is showing transition point, because what you're going to get is boundary layers start off as laminar and then transition to turbulent as you move along surfaces. And then in the transition point now, what they're sort of demonstrating, again with this dashed line here, is you can see it actually takes a bit of a jump there. They want to show that a turbulent boundary layer grows, so increases in thickness, like this here, is getting larger faster than a laminar boundary layer. So that's TBL, turbulent boundary layer. We've got transition labeled as well. Okay, so the turbulent boundary layer gets larger faster, and now the flow, the reason for that label, right, is the flow within the boundary layer is turbulent. Of course, in the laminar boundary layer, the flows are laminar. And finally, we have S here showing that's a separation point. And that's another thing we're going to talk about quite a bit. So part A is really broken down to first talk about boundary layers, what they are, what they mean, how we use them in calculations, basically how they influence designs, and then separation points. Separation points are really critical. Separation, for example, is one of the main factors that influence the movement of pitches in baseball, or the drag on a golf ball, for example. Also, stall, you can have stall on the wings on race cars. You can also have stall on airplanes, which is quite undesirable. So we'll be talking about the different types of pressure situations that lead to separation. So the separation point basically means that's the point where the flow separates. So they've got this solid line shown here now. So the flow separates, it means it no longer stays against the wing here. So where you have flow here at the separation point now, that separates, moves away from the wing, right? And then you have another separation point shown at the bottom here. So the flow moves along here and the flow moves along here at the top, right? So the flow's moving here and here. And then within that region, you're creating a viscous wake, which shows up like a turbulent wake behind these objects. And we'll see a few videos throughout this section, and we'll see that wake coming up, and then the wake is gonna have pressure effects, which will, again, influence things like the drag and lift on objects. So that's S for separation point. And I think finally, just as a more broad overview, I wanna make sure as we walk through section 7, you're aware that boundary layer flows are very complicated, right? This is another thing where if we were gonna describe this mathematically, we'd be doing it in a graduate level course, where you would have had to have seen the full set of differential equations, and then we'd apply those with simplifications in a boundary layer analysis. So we're not focused on the mathematics. We're not overly focused on solving these with all their associated complexities and solving questions about them. Section 7 is much more conceptually focused. So for example, when I'm testing the material we're walking through here, it's the concepts that matter a lot more. So as we go through this, really focus on making sure you understand what's going on conceptually. I'll do a few examples, but they're not the focus of this section. The focus of this section is really telling us how do we make airplanes, race cars, objects moving in flows like sporting balls, and a number of different situations where we have objects located in flows. This type of thing is very practically applicable. So make sure as we go through this, right, the concepts are really making sense to you. And along that note, sort of the big general idea of section 7 is the idea that far away from surfaces, the viscous effects don't really matter. So if you were far away from this airfoil and you had this uniform velocity right here, it would be pretty accurate to use section 4, right? Like that's representative of an inviscid flow situation where you don't have a lot of velocity change that's causing shear in a flow. But when you get close to a surface, of course, now you have the no slip condition, like right against the surface itself. And in that situation, the viscous effects are going to become dominant. So you essentially sort of have two different flows. The flow far away from the airfoil, maybe up here, can be treated as inviscid, and we can solve that fairly simply by, simplifying our governing equations. But close to the airfoil, there's really no way to do that. So close to these objects where the friction forces and the viscous effects are quite dominant, we have to look at a different strategy for calculating these things. And that's why we have what's called a boundary layer. It means that there's a layer close to an object where the viscous forces are important and can't be neglected. And so that's basically why we're breaking this up. Okay, let's watch this video. Okay, so I'll play this video and then I'll pause it as we're walking through it so I can explain it. So I'll pause it here. So the first thing to note is that there's an airfoil within a wind tunnel, and each of these lines here is a different smoke tracer. So you're seeing a smoke tracer, and then you're having flow over this airfoil. So as I push play, the first thing we'll notice is you can sort of see the stagnation point there, right? So there's a smoke line there. You can see the stagnation point. Let me pause it. Okay, and I'll take it back a little bit. So the stagnation point is right around here, and we can actually see, so it sort of flips back and forth as we watch this video. You can see in some cases the flow right here will go down, in some cases it will go up. So the stagnation point is right around this point where we have that zero velocity point. The flow goes either down or up around that stagnation point. I'll bring it back and then hit play again so you can watch that. So we're looking right here. There it is. You see that? So that's the stagnation point right there. Okay, now what they're going to show here with the pulse smoke. Okay, so the point of an airfoil is to generate lift, right? And we know from what we've studied in the course so far, we're going to have an energy balance in these flows. So that means that if you're capable of making a flow go faster or have a higher velocity, what you're going to do then is be able to decrease the pressure. So higher velocity, lower pressure, right? So what we're going to see on an airfoil is as the air comes in over the top of the airfoil, it's going to go faster, meaning you have a lower pressure, and the air is going to slow down on the bottom of the airfoil, right? So down here you have a high pressure, up here you have a low pressure. So below the wing, the high pressure pushes upwards, right? And the low pressure up here causes the force to be in the upwards direction and generates lift. So low pressure here, high pressure here causes the wing to go upwards. And let's see that. It's really neat the way they use the pulse smoke. You can see it quite dramatically. So that's a little bit quick right there. They're going to slow it down in a second. And I'll use the cursor to highlight this. So watch the flow that goes over the top. Right? You're forcing it to go this farther distance, so it's way faster. Look, the flow's already here. This flow is very slow, right? So right along the surface, way faster, way slower here. And you can actually see there's a little bit of a wake, right? There's a little bit of separation there. And look how slow that is. So way faster the air on the top for a much lower pressure on the top. Okay, now they're going to increase angle of attack. Here's where we can really see things like the boundary layers and the separation points. So you're having separation roughly here, and look at how tightly that air is not separating at all. Now you're getting a separation point, and you see the wake forming back here. So the separation point's moving here where there's no flow against the wing anymore, right here. And then as it moves, oh, you see that point? I'll pause it right there. That's what we call stall. Right? So now you're seeing with these smoke tracers, none of them are capable of going down this surface anymore. So you had a point right before this where you were getting very, very high velocity, a lot of lift, and then you basically immediately go upon the point of stall where that boundary layer separates now. None of this flow is against the wing anymore, meaning that their pressure difference is not able to have any forces on the wing. And so you go from a point of maximum lift to essentially no lift. And that's why stall will cause an aircraft to basically just fall straight down. And we can also see as it's paused here, the idea that there's this turbulent wake, within the separation zones, the flow in here is turbulent. So I'll play again and let's watch that, right? So you see the turbulent wake layer right in here, in some of these vortices. So they're going to highlight it now. So as you increase the angle of attack, the lift's going up and up. You're getting higher and higher velocities on top here, slower and slower velocities here. You're getting separation here, 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 and then it's sort of like all of a sudden you had the separation point move up so that it was like at the top of the wing and you had no flow against the top surface anymore. Okay, so that sets the stage now for what we're going to see in section 7. We've got a few things there like boundary layers, separation points, and also some motivation, some understanding of why it's so important to avoid separation because you don't want stall. And when we talk about boundary layers, that's generally related to drag on a surface. So you don't want to be creating too much drag while you're generating lift because that makes it harder for the aircraft to move forward and take off as well, right? Okay, now let's take a closer look at the boundary layer itself. Basic premise for this, right, is far away from this surface, it's okay to use the inviscid approximation. And in that way, it's fairly straightforward for us to be able to describe the flow as we saw in section 4. But viscosity actually matters quite a bit. And the only way you're going to be able to calculate the frictional effects on a surface like this is to consider the viscid effects or the viscous forces. So we say something like viscosity only matters near solid surfaces. And this zone we sort of call the boundary layer. That's what we mean when we say boundary layer. The layer right against the surface where you actually have the viscous forces mattering. So we can see this visually. It's nice to have these velocity profiles plotted. So let's look over at this one first. Before you reach the flat plate, we have a nice even velocity profile. So, out here we say U is constant, and we basically have steady, inviscid, incompressible flow. So because of those things, that means essentially P is constant as well. Right? If velocity is not changing in those inviscid conditions, then we don't have a change in pressure either. So out there in the inviscid space, we can calculate those flows, and then we see the shaded region with the thickness denoted as this delta right here, that's what we call the boundary layer. Within this dashed line, I'll trace over that, right? And now it becomes sort of evident to us as well that above this boundary layer, you don't have viscous effects, right? Because there's no change in velocity. But then within that boundary layer, there's a velocity gradient where the viscous effects are going to be very important. Now, some terminology. So generally we say leading edge, right, to denote the front. And this is, we're looking at a flat plate here. We'll talk about different shaped surfaces, but it's best to start with the most simple case. Then we've got the laminar boundary layer shown here, right? A certain portion from the leading edge will develop as a laminar boundary layer first, and then you'll reach a point of transition, which is shown again with the increased growth. That's how we generally show it, because at the transition point here, the thickness increases faster in a turbulent boundary layer. So then you have turbulent boundary layer from here on in. And as we saw, in section 6, there's some real basic differences in treating laminar things and turbulent things, right? So when the flow is laminar, we tend to be able to use the analytical expressions, and the mathematics are a little more simple. And then turbulent, we move to experimental measurements. So we know, of course, denoting laminar boundary layer and turbulent boundary layer, there's going to be sort of two slightly different ways we'll solve for these things, depending on the nature of the boundary layer. One other thing in this case is we use a Reynolds number shown here with a little x on it, denoting that it's a local Reynolds number. So it's a function of the x position. Now, we have our x equals 0 as the leading edge, and then our x direction is this way, shown actually here, right? So it means that the Reynolds number will change as we move along this plate. As x increases, right, Reynolds number will increase as well. And so it's a slightly different way of thinking about the Reynolds number, but we know, because we're talking about a situation in boundary layers here where we're discussing when the viscous effects are important. So it's, again, we know the Reynolds number is a comparison of viscous and inertial forces. So this is another situation where the Reynolds number becomes important. Now, I should mention that every case is different, and these Reynolds numbers will depend quite a bit on things like heat transfer properties or surface roughness, right? So that's why this approximately equal to sign should be taken very generously here. So when we say the Reynolds critical number is like approximately 500,000, for this transition point, that's a very loose 500,000, right? That's just an approximation. So it really varies, case by case. Just think of that as an example. Okay, so that sets the stage for boundary layers. Hopefully you've labeled this a little more than I have here, right? Remember to keep in mind that self-initiated motor skills is what gets you retention on these things. I have notes that say, for example, within this blue region, you have shear, here, no shear. You can have things like that written down to make sure you recognize this. Now, I think it's going to become apparent, right, that these boundary layers are very important, and it's going to be important to know how thick they are. So it's just sort of generically shown here with this little delta. But we're really going to want to know how far above the surface does this boundary layer extend, right? That's the first thing that's going to be of importance for us. Okay, so that's the following section here. Okay, and we have multiple ways of describing the boundary layer thickness. So the first one shown in A there, this delta, is what we call the disturbance thickness. And that's defined in a way that's sort of easy to understand, but very challenging to really measure or use in practice. So we basically say you have lowercase u there is like the local velocity. So you say the point at which that's 99% of your free stream velocity. Capital U, you remember, that's the velocity far away from the surface. When you reach 99% of that, you say, okay, that's where we decide that the boundary layer stops. Okay, and that we denote as delta. So everything within that is boundary layer, outside of that's not boundary layer, right? So viscous effects matter in that region and they don't matter outside of it. But that's a great definition and a little more tricky in practice. So we have other definitions. In B here, in this example, we have what's called the displacement thickness, denoted as this delta star, displacement thickness. And what we're doing there is, so you have, this is what the actual flow looks like in this one here, right? So the flow slows down near the surface because of the no slip condition, right? So you basically have this region that's shaded in, and what we're looking at there is, because the flow is slower there, it's slower than what this u, this right here is our u velocity, right? It's slower than the u velocity. So because of that, we have a decrease in the mass flow rate, that's happening across this region here. That's caused by the fact that the velocity is slower, right? There's less mass flow rate there. So we define a displacement thickness as saying it's the height or the distance away from the surface that would generate an area, right, that exactly balances out the mass flow that we're losing from the no slip condition, from the viscous effects there,
if you were to treat the velocity as traveling at that u velocity here, right? So now we have this area matches this area here, and that's defined as the displacement thickness. Now you can see from the visualization, it's not the same as the disturbance thickness, but what a displacement thickness helps us do is to sort of compare different situations of boundary layer thickness. So if the boundary layer effects are higher, then you have a thicker displacement thickness, meaning that there's more of a disruption, more of a slowdown that's causing your mass flow rate to slow down. So we'll talk about the math quickly here. Again, not because we're going to do calculations with this and focus on that, but more because we want to know how we get these concepts. So if you're running experiments, for example, you want to be able to get the displacement thickness. It pays to know a little bit about how this mathematics works. So if we look at this area here and come down here, we know the loss of mass flux there is going to be a mass flow rate, which is rho v times dA, or density times velocity times the area. We don't have to integrate in this case because there isn't a change in velocity over the area. So you basically end up with the rho and the v, the density times the velocity, and then the area that's perpendicular to this flow. If you think of like looking right here, if you're looking that way, the same way the flow is traveling, it's going to be that height, that delta star, times the width of the plate. So that's your mass flow rate in this case. And then if we equate that with, so in this case, your velocity, this, right? So this velocity from here to here, for example, is the free stream velocity, capital U minus the little u, where the lowercase u is like these guys here, the actual local velocity, right? So if you want to figure out the mass flow rate across this, I'll highlight it in green, right? If you want to do that one, then you take instead the density times the velocity. The velocity is now the u minus u, and then you do have to integrate over the area because the velocity changes over that area. So now instead of a fixed height, you do a dy. Y direction I'll label more clearly is that one. And then the width again, normal to the page we're looking at here, right? So across the plate. Then you just rearrange that, and we've got this nice expression here for how you would go about calculating the displacement thickness. Now in the y direction, this is often written as delta because you don't have to integrate the whole thing, because once you're sort of at the edge of wherever this boundary layer is, you don't have to go all the way, right? You just go far enough, because at a certain point, this u minus u is 0. So like once you're up here, that just becomes u minus u, right? So that equals 0. So you really only have to integrate up sort of a meaningful distance away from the plate to figure out what this displacement thickness is. Okay, then for our third one, we can reference the picture at the bottom. So showing again the mass flux displacement thickness, right, where you have the distance away from the plate due to mass flux, disturbance thickness, right? That 99% of the free stream velocity definition. And we have a third one that's theta, that's the momentum thickness. So pretty much the exact same idea as the displacement thickness, except displacement thickness says, okay, our mass flow rate's decreased because the velocity is slower closer to the plate. And the momentum thickness basically says, well, the momentum flux also decreases because you have decreased velocity near the plate. And so you define that sort of mathematically in the exact same way, where you can say, you know, what's the momentum flux across this region sort of here, right? Versus the momentum flux decrease that was caused by the fact that there's a boundary layer. Rearrange that again, and that's how you can sort of practically calculate. Generally, that's done with experimental data, I'll note as well, because it's quite complicated to get meaningful values for this. So that's how you would go about calculating a momentum thickness. Much, much, much more important for us to just focus on the idea of what displacement thickness is and momentum thickness is. What does it mean? And so it's just like saying displacement thickness. It's just like saying the wall's really here, right? But because there's a boundary layer, if we considered the wall to move up here, this displacement thickness distance instead, and then all the flow was considered to be the free stream velocity, right? This distance here would account for the fact that we have a mass flux decrease caused by our boundary layer. So it would be like the wall would kind of really be right here in this flow to basically counterbalance the fact that we have a decreased mass flux because of our boundary layer.
So here's where I would do a quick example to show how this can be used in practice. And I've included that now as a separate video. And that just kind of shows us one of the ways in which displacement thickness could be used. Okay, so next we're going to look at pressure gradients in boundary layer flow. And essentially what we're doing with this is we're looking at the concept of separation. And I've put a definition there to kick us off here. Flow separation is the detachment of a boundary layer from a surface into a wake. So that sort of puts in words what we saw from our earlier airfoil video. So we're going to look now at the details of how we end up with separation, what exactly is happening there. And then as engineers, we'll look at, are there any ways we could control it or maybe delay the separation? So that's what we're going to do in this section here.
So we've talked a little bit before about pressure gradients and their influence on the flow. So I'll give you a quick second to think about this yourself, right? If I have a fluid that's flowing and I'm driving that flow with pressure, does that mean the fluid's flowing from a high pressure to a lower pressure, or is the fluid flowing from a lower pressure to a higher pressure? Okay, so think about that. Pause it if you need to. If you're driving a flow forward, it means you're going from a higher pressure to a lower pressure, right? So that higher pressure is going to then push the flow forward. So I'll maybe make a little note of that, right? If you have some fluid flowing with some velocity, you're basically, if you're pressure driving this flow, it's from high pressure to low pressure, right? And so the way we write this, because the pressure is going from high to low, the pressure is actually decreasing along the flow direction, right? So we say that's when the dp dx is less than 0, right? So the pressure is going from high to low, it's decreasing. We call that a favorable pressure gradient because it's favorable because that's gonna help the flow in the direction that it's going. So it's favorable for the flow because it helps move the flow along, right?
Then we could also have, of course, no pressure gradient, or the pressure gradient is equal to 0. So that naturally doesn't cause the flow to accelerate, but it also doesn't cause the flow to decelerate. And then we have the case
where you're actually going from a low pressure to a high pressure, right? That'd be a positive pressure gradient because the pressure gradient is going from low pressure to a high pressure, so it's increasing. So we say dp dx is greater than 0. That's called an adverse pressure gradient. We call that an adverse pressure gradient because that hinders the flow, right? So that's going to cause the flow to slow down because the fluid particles are not going to want to flow from a low pressure zone to a high pressure zone. So the adverse pressure gradients then slow down the flow. So you should have some kind of notes there, but just in case, don't copy what I'm writing, right? Just like have your own summary. But you should have something that sort of denotes that like U is increasing here when it's favorable, and when it's adverse, U is decreasing. So the note we're going to kind of make here is, in the case where it's decreasing, the particles can be brought to rest. So you can actually decrease the velocity so much that you can stop the flow. Now, stopping the flow is what's causing the separation. So this leads directly into flow separation. If you have an adverse pressure gradient that is large enough, you'll decrease the velocity so much that it actually causes the flow to stop. And in a flow separation situation, so let's say I have a surface that looks like this, and my velocity is going this way, and then I have my fluid particles flowing along, and then all of a sudden the adverse pressure gradient is so high that it causes the particles to stop. Well, to balance mass flow, there's particles coming behind them, so they have to move out of the way, but they can't keep moving forward, so generally that's where they'll move away from the surface. And this is why we say for flow separation, particles are forced away from the surface. We'll talk about that more and look at examples of this like we saw in the video earlier as we march through this section more. So it's important to get the terminology right, so favorable and adverse pressure gradients, but also to know when the pressure gradient is negative, that's a favorable one, and when the pressure gradient is positive, that's an adverse one. So definitely make sure, again, as we're walking through this, you really deeply understand these concepts and why you can just look at an equation like that and say, based on what your pressure gradient is, you know if it's a favorable one or an adverse one. Okay, so moving along here to this figure right here. So we're basically saying adverse, guys, you could, not necessarily have separation, right? So how do we figure out when we do or don't have separation? So we've got this nice figure here to help us out, and it's always best, I think, to do these things visually. So in looking at this figure, you basically have region 1, region 2, and region 3. So in region 1, right here, in this zone, you're going from a larger area to a smaller area, right? When you go from a larger area to a smaller area and you're conserving mass, it means you're having an acceleration, right? So the velocity is going up in this zone, means that pressure must be going down. If pressure is going down, right, your pressure gradient's negative, so you're going from a high pressure to a low pressure, so that guy is favorable. Second region, no change at all, right? Area at the beginning, area at the end is the same, so region 2 is that 0 pressure gradient. And then region 3, this is where we're getting the adverse guys, right here, because we're going from this small area to a larger area. Therefore, velocity slowing down, and that velocity slowing down means you must have pressure going up, meaning that you potentially have a higher pressure over here, higher pressure here, and potentially a lower pressure here. So that's adverse. That's no good at all. Now, region 1 and 2 are totally fine. Different color time. Because with these pressure gradients, there's no chance of us decelerating the flow in those regions. So there's no possibility that we slow the flow down enough to cause the particles to stop. Region 3, what exactly is going on here is we have, because of the no slip condition right here, we're slowing down the velocity, right? So you're seeing like this velocity profile here is indicating that the velocity is slow near the wall. Now, what happens is if you also have this adverse pressure gradient, you're also causing the flow to decelerate, to slow down because of the pressures. Now, that slowing down of the flow is going to be most problematic at these lower velocities right here, right? So what happens is as you slow the flow down, you get a curve that starts to look like this guy here, right? Because you slowed down all these velocities right near the wall. And once you have that gradient in velocity, see how that's basically straight right there? Now that is where we get a separation point, because that means that that velocity gradient is now 0, right? So where that slope becomes straight, that velocity gradient near the wall becomes 0, and that's our separation point. That's how we define separation, because as you see from this dashed line now, you can't have any flow. You don't have any velocity moving forward, no velocities moving forward here, and you're getting this backflow region here where this pressure is actually pushing back now. We saw some examples of adverse pressure gradients, what it can do to the flow between parallel plates. So we know that the pressure is going to start to push the flow backwards, so you're going to get this backflow right in this region where the flow is actually going this way, and this flow is going this way. So the only way that you can have mass conserved when this flow is going this way, they're coming towards each other, right, is for that flow to go away, right? So that flow is going away from the surface there. That's called separation. Right, so that flow, you have this dashed line right in there, you're getting backflow or vortices, and you're not getting any of the flow sticking against the surface anymore, helping change the surface forces that we rely upon the flow for, so things like particularly for lift, right? So that's exactly what is going on. So that's why we can have separation in region 3. So that leads us to the question, can we prevent or delay separation? All right, now we're going to look at laminar and turbulent flows and understand how they behave when it comes to separation. So these plots show us the velocity profiles when you're dealing with laminar and turbulent flows. And we've learned previously, like in section 6, for example, that you're going to have a more blunt profile when you look at the turbulent one, and laminar is going to tend to be more parabolic, more gradual as you move away from the surface. So we're looking at velocity profiles here. So this is plotting velocity. We oftentimes draw like the arrows in here. So that's the laminar one. That's what that's looking at. And then this is saying your distance y away from the wall, where at like 1.0, you're at the edge of the boundary layer because we're scaling to the delta right here. We're scaling to the boundary layer thickness. So it means within the boundary layer, in the laminar flows, you have a gradual difference. And in the turbulent profile, you're getting like right near the wall here. See that? See that change in the velocity right there? It's much more dramatic right near the wall in the turbulent profile. So the question is, which one's better? Or which one is going to be capable of delaying separation more? Well, we also plot momentum flux profiles. And so we see, again, if we plot the momentum flux that we're saying there, that's mass flow rate times velocity. We've seen in the past that has a u squared dependency, so you plot that u squared here. Now it becomes even more evident when you look at the momentum, right? You compare turbulent there to laminar there. So right near the surface, close to the surface here, actually the turbulent flow has quite a bit more momentum, right? So if you just took a look, like let's say pretty close to the surface, let's look right here, we're pretty close to the surface. So that's the laminar momentum, that's the turbulent, a lot more momentum in the turbulent flow, right? So the separation occurs when the momentum at the surface is reduced to 0. And that's the kind of thing, hopefully you just jotted down, but let's just do it anyways. So separation when momentum at surface is reduced to 0. And so as we can see right here, the turbulent flows have quite a bit more momentum, right? And they're able to distribute that momentum because of the turbulence. So turbulent momentum is higher. Therefore, a turbulent flow is much better able to resist having separation. Now, exactly when does that occur? Well, unfortunately, we don't have numbers for that because that's going to be heavily dependent on your situation. So things like surface roughness, defects, and that sort of thing, they heavily influence when your separation occurs. So what we've gained from this section then is a very qualitative understanding. Qualitative meaning that it's basically descriptive in nature. You describe the quality, whereas conversely, quantitatively would be if we had numbers to put to it. So we're going to end here with a qualitative description of separation, basically saying when you have an adverse gradient, it is possible. If you want to know exactly, specifically when, you have to run experiments basically or use some high-level CFD. Or if you're looking at generic shapes, we'll talk a little bit more about this later when we talk about the specific geometries and we look at drag. We'll look at things like some common shapes, spheres, and cylinders, and we'll talk about what we know about separation in those cases because we do have the experiments already done for very simple geometries, right? We'll talk about that later. What's really important to understand here, though, is things like if you want to delay separation, if you want to make it much less likely for separation to occur along a surface, you definitely want to have turbulent flow, right? That's what these plots are showing us. So make sure before moving on to the next section that you've really got this, right? So you know exactly what separation does, exactly what an adverse pressure gradient means, right? Also understanding that an adverse pressure gradient generally is because you have, like we saw in region 3 of that picture, when you have a cross-sectional area that's increasing, right? That's generally going to lead to adverse pressure gradients, right? So in cases like that, if you want to prevent separation, you can use turbulence as sort of your first line of defense to prevent or delay separation. Okay, so that's the end of part A, where we look at boundary layers. Just a quick summary here. We looked at some features of boundary layers and how they're defined and how they're the region where the viscous effects are dominant. And they're going to be really important as we talk about the forces for these external flows, so flows over objects. We looked quickly at how you define different thicknesses of boundary layers. And then very importantly, we looked at the concept of separation, right? And how separation occurs from adverse pressure gradients. And they basically come about because you have like an increase in the cross-sectional area of where your flow is flowing. Yeah, and like we just said, turbulent flows are better able to resist separation. So a strategy if you wanted to delay your separation is to have a turbulent flow instead of a laminar flow. And we saw a nice example video of an airfoil there that showed many of the important features of these boundary layers. And in general, separation means like when the flow is not attached, so there's no flow right against your surface anymore, so we don't get those forces. So that leads to very catastrophic things like stall on wings, for example. And we'll see in the next few videos as we go through to part B, also a big impact on drag. So that's why it's important to have strategies to know if we could sort of delay that or not. Okay, and that's all for video number 19.
Bye-bye.